I'm Saab Thaliwal, Chair of Metro Vancouver's Board of Directors, and I would like to start today's event in a good way by acknowledging that our region's residents live, work, and learn on the shared territories of many Indigenous peoples, including 10 local First Nations. Climate action is one of our highest priorities at Metro Vancouver. For more than 20 years, Metro Vancouver and its members have taken a leadership role in responding to climate change. We have made efforts to reduce greenhouse gas emissions, set stringent targets, declared climate emergencies, and many of us have achieved corporate carbon neutrality as Metro Vancouver did in 2019. Today's conversation is about the Thwaites Glacier in Antarctica. This glacier's anticipated collapse has worldwide implications. I look forward to hearing Professor Holland's insights and advice on what we can do to prepare. Here to introduce today's special guest is Adrian Carr, Chair of Metro Vancouver's Climate Action Committee and a councillor for the City of Vancouver. Dr. Carr is a longtime climate activist and extremely well-versed in the environmental issues affecting our region. Her passion for climate action is unmatched, and we are fortunate to have her guiding today's discussion. Dr. Carr?
Thank you, Chair Dhaliwal, for that introduction. Like many people, for many decades, I've been advocating for the health of our planet, and that despite the efforts of so many, we are in a climate emergency. As Chair Dhaliwal mentioned, taking action on climate change is a priority of the highest order for Metro Vancouver. Through plans such as our Metro Vancouver Climate Strategy, which we're calling Climate 2050, we are striving to ensure regional infrastructure, ecosystems, and communities are resilient to the impacts of climate change, and we absolutely have to be successful. For my colleagues in government joining us today, I hope today's conversation will leave you with a better understanding of why it's so important that we work hard and take more dramatic action to protect our planet and our future. When we hear about glaciers melting in Antarctica, it can sometimes feel like a faraway problem. However, since the beginning of the 20th century, sea level has risen by 20 centimeters, and over the next 80 years, it could rise by a meter or more. Today, we have the unique privilege to hear firsthand how the climate crisis is impacting global communities such as ours. I am pleased to welcome Professor David Holland, Director of the Center for Global Sea Level Change, who joins us from an icebreaker that has recently departed Antarctica. Professor Holland studies atmospheric ocean sciences at New York University and is a leading researcher on the global initiative to study the Thwaites Glacier, sometimes called the Doomsday Glacier. We're thrilled that David is able to join us today, and now I'll turn things over to Metro Vancouver's Commissioner, Jerry Dobrovony, who will moderate this afternoon's discussion.
Thank you very much, Director Carr and Director Dhaliwal, Chair Dhaliwal, and thank you everyone for joining us today. I'm Jerry Dobrovony. I'm the Commissioner and CAO here at Metro Vancouver, and it's my privilege today to help facilitate the questions. As David is joining us by satellite phone, we'll help him know that the call hasn't dropped by ending our comments with over, and you'll notice there may be a slight pause in our interaction. We may lose him during the call, and if this happens, please stay with us as he will call us right back. We have a few questions to start off with, and then we'll open the floor for questions for everybody that's on the Zoom line, and we'll ask you to use the raise hand function in Zoom, and I'll field those questions as we go. So hello, David, and welcome. Thank you very much for joining us, and can you please tell us a bit more about yourself and your research? Over.
Thank you. I'm glad to be able to join you today. Today is the last day of the science cruise. At midnight tonight, we leave the coastline of Antarctica and head north, somewhere warm like New Zealand. It's been an amazing almost 2 months now here at the bottom of the Earth. It certainly changes one's perspective on pretty much everything. So myself, I grew up in Newfoundland, and I was educated there graduate school at McGill University, and then I ended up as a professor in New York University. My entire career and life has been consumed and fascinated by ice, playing ice hockey, skating on ponds, and later my PhD was about Arctic sea ice. And I have to check every now and then if you're still there, so I could just do a check.
Yes, we're here. Thank you very much. Over.
Okay. And so I became fascinated as a young person with the Canadian Arctic and how it was discovered. It was discovered by incredible hardship and achievements. And that really, I've always been very much a mathematician and scientist, but fascinated by ice. So my PhD was about the Arctic sea ice in the early 90s. And what's remarkable to me is when I did my PhD on Arctic sea ice computer modeling, and no one on this planet spoke a word in the early 90s that the Arctic sea ice on the planet would ever change in our lifetime. And within 5 years, it became clear that it was disappearing, to the point now, some decades later, half of the Arctic sea ice is gone, which is outside the realm of anything anyone would have thought a few decades ago. So the polar regions of Earth are particularly sensitive because they're either white with ice, and if there's no ice, then they're blue with ocean. So they either keep the planet cold or they warm it up. So they're particularly vulnerable. So we've seen that happen in the Arctic. Check?
Yes, we're still here. Over.
And so then I became interested in the Antarctic because of the massive amount of ice. Typically, through time, the last millions of years, Canada is most of the time is under an ice sheet, like the one here. So I'm standing about 100 meters from the coastline of Antarctica. There's a giant ice wall, a barrier here, an ice shelf. Yesterday, there were two of the cutest possible penguins staring at us for 12 hours straight, wondering what are we doing here in this red object floating here. And being here, this ice sheet, as I mentioned, the one in Canada is gone now because we're all living there, obviously. But it's natural for ice sheets to come and go on the planet, and it's natural for sea level to go up and down almost like 100 meters through long periods of time. There's also evidence in the past that sea level has changed suddenly by several meters on this planet within a century. So we can see that in the past records. So all things are possible. And what really motivates my research is to try to figure out whether or not the Antarctic ice sheet, or parts of it, could undergo rapid disintegration within this century. And to me, that's a fascinating scientific question because it's really trying to understand how our planet works. And what I and my colleagues have been learning in the last few decades is that kind of if you warm the planet, then ice will melt, is kind of the bottom line. And that seems so obvious, but it's not. Our planet is a very complex system involving basically the atmosphere, the ocean, and the ice on the planet. And these three large fluids interact. The short summary of the decades of research is what we've learned is that ice can collapse if warm ocean currents run into it. So that we always thought it was a warm atmosphere that would kill the ice sheets. But no, it's warm ocean currents that get moved and directed towards ice sheets. That's one link. There's only 2 or 3 more links. But the ocean currents are controlled entirely by the atmospheric wind. And the winds have been changing. And the winds are controlled by only one thing on our planet, and that's the air temperature. And the air temperature changes naturally, but we've also been changing it. So if I go the other way, on this little tiny planet we live on, if you change air temperature, you change wind, you muck about with ocean currents, and if they run into big ice sheets, they're toast. And that's the bottom line of what seems to be unfolding in front of our eyes, is that this part of West Antarctica is undergoing the biggest change anywhere on Earth. Its elevation is dropped because the ocean are going under it, and as we measured last week, they're warm. Over.
Still here. Over.
Okay, so that's kind of the science thing is, and here comes a helicopter. I don't have to get on that one for another half hour. So, so that's the science story is we're learning how the planet works, and what we're learning is that we don't know a lot, and that we're learning that massive, surprising changes can happen naturally, and from computer modeling, we can also see now that greenhouse gases are also affecting this ice sheet. So we've been here for the last while, drilling through the ice sheet with a hot water drill to access the ocean that's now underneath it. And we found that there's very warm water underneath it, and that means trouble for that glacier. Over.
We're still here, over.
And so that's a science story. But the real drama is, just like we have a weather forecast, we look on our smartphone and we can see the weather tomorrow. That technology has been developed since World War II. And every day we do a weather forecast and we collect airport temperature measurements like at Vancouver Airport, everywhere around the world, and we refine our understanding of the atmosphere. And so we've become pretty good as a global society with weather prediction, but we are a very long ways away from a global ice forecast system, which is a way more difficult problem to forecast what is going to happen to Antarctica. And that's really the thrust of our research. And there's a pilot landing behind me, Bishop from Vancouver, one of our Canadian pilots, people with absolutely amazing skill. Yesterday they Thwaites Glacier to put some probes in, and it is unbelievable. It's like craters on the moon, and we were flying through a landscape. And in doing all that, we hope that we'll come to an understanding of how this works. Earth collapse into the ocean and raise sea level by a meter, or if its neighbors go more meters, ultimately up to 10 meters, which would rearrange the coastline on the entire planet. So those things do happen, and they can happen, and bits of it seem to be unfolding right now. Over.
Great. Yeah, we're still here. Would you like us to shift into questions?
Yes, please.
Okay.
Over.
Thank you. Director Carr, would you like to start?
Well, this is fascinating. I've got about a bazillion questions from what you've said. But one of the things, if you don't mind explaining again, you said that the Antarctic elevation has dropped, but I think it wasn't clear. It was a bit muffled by how much. I'm interested in that, as well as your statement about the warm water under Thwaites and whether Antarctica itself has dropped. Those comments you made, if you could explain those a little bit more fully and tell us what scientifically is going on down there with the elevation drop and the warm water.
Okay, so if you picture when Canada was covered in an ice sheet about the size of the one that's next to me here, the Antarctic ice sheet, then that ice sheet was so big, several kilometers thick, that it's so big in that it flows towards the coastline. And so you picture it, it's covering British Columbia or parts of it, or Eastern Canada, and that glacier flows towards the ocean, and then it flows out onto the ocean by gravity. But water is unique in that solid water, which we call ice, floats, and I think it might be the only substance in the universe that does that. It's lighter than its liquid, so ice floats. And so all around me here are these massive walls of ice where the Antarctic continent has poured out into the Pacific Ocean and has these vast ice sheets, which are the scale of like the province of British Columbia, these massive pieces of ice, and the Pacific Ocean is underneath them. So where we drilled last week, we drilled 500 meters through the ice shelf, which is floating, if you will, off the coast of British Columbia by analogy, down into the ocean, which is 1,000 meters of water beneath, and we're probing that water to see if it's cold or warm. So clearly, if water under ice is above freezing, the ice cannot sustain. And we're finding in this spot in Antarctica, the water is 3 degrees Celsius above the freezing point, which is absolutely massive. So the ice that I was standing on is melting from the bottom. And so it's melting in some places by 100 meters per year, which is an enormous number. It's the largest melt anywhere on Earth of such a thing. And so the surface we're standing on is dropping by meters per year. So picture something the size of, say, British Columbia, that scale, and it's meters per year. It's dropping because it's melting from below as the ocean goes under it. That's why this has garnished worldwide attention. When satellites first looked over the planet and they noticed this spot was basically something dramatic was happening. But from satellite, you can only see elevation drop. We've come here to drill through it as we suspected. The ocean now is warm under it, which is something different because it cannot have been happening very long or Antarctica would not be here. So this could be natural, could be human. Computer models suggest right now it's both, which I find it surprising that we can change greenhouse gases and have an impact all the way down here in front of this ice. Over.
I have a second question for you related to what you've just said. There's been some estimates that the Thwaites ice shelf only has a certain number of years before it does melt and thus unleash Mother Ice and melt from Antarctica. Do you have any estimate based on the temperature range that you've just identified, any sense of projections around how long the Thwaites will last?
Right. So I think there was some. I saw that in December before I came here. I think there's some confusion there, which I'll try to clarify. So an ice shelf is a large object, very large, that's floating on the ocean. Something like I said, maybe the scale of British Columbia, and it's holding back. So picture a large object floating off the coast of BC. Very thick, very large, and then picture this massive amount of ice over Canada, the grounded ice over the land of Canada, the continent. It turns out ice shelves act as a cork, like a wine bottle on its side, that holds back the inland ice. And so if that cork pops, then the inland ice tends to rush toward the ocean and add to sea level. The number somebody came up with of 5 years was that the Thwaites ice shelf could in fact disappear within 5 years because it's beginning to fracture. It all sounds complicated, but it's really simple. If warm water goes under ice, ice melts, it starts to crack and break up. So then the question is, if the ice shelf goes in a few years or a decade, what happens to the inland ice? And that's really the absolutely fascinating story. Jack, you still there?
Yes, go ahead. We can hear you.
So as I look south towards South Pole, there's a guy, a friend of ours, Denise and I, Charlie Bentley, PhD student in the 50s. He came here and he, for his PhD, discovered that West Antarctica is actually all of the Antarctic ice sheet is below sea level. So it's like if you picture ice over Canada, well, Canada is above sea level by definition. But if you picture an ice sheet over Canada that spilled out into the Pacific Ocean, covered a large the North Pacific, then that ice sheet would actually be on a seafloor, not on land. So what we're looking at in West Antarctica is a huge piece of continent that's actually in the ocean already. That's why it's, and this PhD student accidentally discovered in the 50s, he couldn't believe it, that this vast piece of ice, when you go from where I am on the continent of Antarctica at the coast, as I look towards South Pole, about 1,000 miles south, the seafloor becomes deeper and deeper and deeper, and the ice becomes more massive. And so all of that ice is subject to being attacked or melted by the ocean. One other thing, not for now, is that there's, if you're familiar with instabilities in physics or whatever, like if I have a hill and I put a ball on top of that hill, if I touch it, it's unstable mathematically, the ball will roll down the hill. West Antarctica is just that. If you give it a little nudge, it's unstable. And right now it's on a little piece of subseafloor mountain, which is just south of me, and that mountain is kind of holding the ice shelf in place. But should that melt beyond that point, there are no more pinning points until Thwaites pretty much reaches the south pole of the planet. So there's nothing to stop it once it starts. And it's really bizarro that that place that was identified decades ago mathematically and observationally is the most unstable place on Earth. It's ironic that that's the part of Antarctica today that has a warm jet of ocean current going under it. It's very weird, but it is happening. Over.
Okay, my final question is, given what you've just explained about the ice shelf and the Antarctica itself, what does your research tell us about the potential sea level rise, especially if we don't keep to 1.5 degrees global warming?
Right, so that's the part where I think society wants answers, and I appreciate that. We all do. I don't think society appreciates the difference between a weather forecast, which we as a world endless observations and theoretical and computational developments. For example, the Canadian weather model is one of the best in the world, and it's taken enormous efforts to create. But the earlier chain of events, insert effect ocean effects glacier. We really don't have ocean forecasts. We don't understand chaos theory of the ocean. We don't understand large ice sheets and how they react. We have no forecast going forward of how the weather will change the ocean when the ocean will change the glacier. It is a difficult message perhaps to hear, but we are, nature is powerful, and I'm certainly humbled in her presence here, as I have been for the last month, as she has blocked our progress towards Thwaites with massive sea ice and icebergs and weather. But we are a distance away from a smartphone app, if you will, that says, when is sea level going to be what? Right now, we can just say there are some interesting signs, shall we say, of change happening here, the largest on the planet. And it's very plausible that Thwaites will put meters in the sea over decades, centuries, and beyond. We just don't know. And it's like 1952 at Princeton University, the first computer made the first weather forecast, and it was awful, but people were jumping for joy with the insight that something was possible. And so we're just touching that possibility now we're at the very early stages of understanding the southern part of our planet. Check?
We're still here. Over.
Okay. So what it particularly speaks to is Canada's role in the world. As a Canadian, I can speak to Canadian education, and Canadian education in the environmental sciences is second to nobody on Earth. So we do love the environment, and we love it to observe it and play in it, but we also love to understand it and study it. And we're particularly good at cold places because Canada has a bit of cold weather. And so I think we have a particular contribution to make, not only in the math and science of understanding our planet and addressing this problem, but it's our entire skill set that we bring to the world. We have our pilots here who have been flying us around safely, and we've achieved a world first here. This is the first time ever we've brought in new technology to study this problem. We brought, with our South Korean colleagues who have this icebreaker I'm on, we brought Canadian helicopters, and more importantly, their pilots, and we've been able to bring 50 tons of hot water drill equipment onto an ice shelf, access it, drill through it, and put a weather station, an ocean weather station, through it to begin to monitor, which it's working. So those kind of steps forward, I think, speak volumes of Canada, from my point of view, contributing its talent, its resources, its people, from science, engineering, to everything, the pilots. In doing this to help address this question and get to an answer, we do not have an answer. We're certainly seeking one. Whether we get there in time is a question. I don't think people understand this is the single most difficult place on this planet to work, Antarctica. We failed in our attempt to get to Thwaites this year. We had to go to the next glacier because the icebreaker could only get so far traveling. This is a massive monster icebreaker, but it could only get too far into the sea ice. And we couldn't get close enough with our helicopters to get onto Thwaites, so we got onto the next glacier and did our research, kind of a plan B. And so people need to understand that getting the science done here is slow work and it's dangerous. In the last decade, a handful of my colleagues have come here and not come back, including 3 Canadian pilots who never made it out. So it's fascinating science. It's extremely dangerous. It's important, and I would like to communicate that I'm not sure people understand. To get to the answer, the forecast is going to cost time and much more than that even. Over.
Thank you, Professor Holland. I have 2 quick questions for you. First, why should coastal communities be concerned of the Thwaites ice melt? And can you talk about specific effects on Metro Vancouver and Pacific Northwest? Over.
Over. So there's 2 parts to that. One is that if you picture the South Pole of the Earth and Antarctica, picture it as a very large ice cube that's very large, and it's hard to get your head around that melting it will distribute water over the whole planet in a very short time. So some people seem to think it's something far away and it will take forever. That's not the case. The water that gets distributed around the planet, if we just take a meter, 3 feet of water, well, everywhere from Victoria Harbor to St. John's Harbor will notice a meter of water. But there are other particular parts of eastern and western Canada. For example, Nova Scotia may become an island like Newfoundland, and parts of southern BC are quite low, and so adding a meter or ultimately meters of water will change that landscape. And it's not only the physical structure. We like to, go to the beach and live at the beach. We build houses and around the world at the beach, but it also can have a profound impact on the ecosystems that live there, as they may not respond to a rapid change of salt water coming inland. So everything from the ecosystem to our living systems, and anywhere that we go around the planet and see low coastline, including South BC, and I'm not totally familiar with the details of the coast of BC. I'm sure we could produce an elevation map and find out where and what would be impacted. And from my point of view, the rest of the whole planet, since we're all in this game together as we warm the planet, states like Florida will be almost wiped away eventually. Countries like Bangladesh, major cities like New York, Shanghai, on and on and on. All of these amazing structures we built, we never thought about this issue that sea level changes naturally and also by our hand. So it is a Canadian issue, and it's also our responsibility as Canadians to think about it as a planetary, global issue. Over.
Thank you, Professor Holland. And finally, my second question is, what do you want local government leaders to consider or take away? Over.
I think, I would say that the biggest thing to consider or appreciate, like that. Okay. So I just got a message that my flight has been canceled, which is really good news because I don't want to fly out in the sky in front of me. That would be scary. So, what was the question again, please?
The question is, what do you want? Yes. What do you want local government leaders to consider or take away from this discussion? Over.
I think it's probably something. It's one has to be careful to separate my opinion from scientific fact. So I'll first give you scientific fact and then my opinion. We'll try to separate the two. More than anything, we need to value the value of science, and we need to be very critical of science, and we need to really get the science right. And so in Canada, we are, in my humble words, I think we're leaders in that, and we're excellent at that. And we need to never let go of that. no matter what the outcome is, if one wonderful thing to learn here over the coming years is that Thwaites is not a problem, then that would be fabulous, and science will lead us to that. So even though it's called the Doomsday Glacier, it gets attention, and more likely than not, it is that. I want people, and Canadians are really well tuned into that, is science has great value. And that only has value because of Canada's people and our investment in our students in science, technology, engineering, mathematics, and our investment in skills and our pilots and all the people who make our equipment and instrumentation. That investment not only makes Canada help the world, but it helps Canada help itself. For instance, the instrumentation that we put under the ice shelf was built by a company in Ottawa, which is becoming an up and world leader in technology in monitoring the ocean. And those guys have been working with us. And when we finally put the instruments in, and I got a text message back from Ottawa that says everything's working, I was somewhere between tears and cheers for a while. So I think it's this, for me, the message is one of not to take our foot off the pedal of being global leaders in the environment, particularly through our development of our people in all the spectrum that is. So that would be my message, is that, and more important perhaps than the science, is that our people in science and everything to support it really matter. Over.
Great. Well, thank you very much, Dr. Holland. We've got a number of hands going up now, and so I'll ask Director Hawking to go next with his questions.
Thank you so much, Dr. Holland. This is extremely interesting. Really appreciate you taking the time to talk to us, and of course, the work that you're doing. And now, as a member of local government, it's as the rest of us are here, it's really important for us to get an understanding of, what are the best estimates of sea level rise over the century that's before us. And looking at the IPCC's work, the estimates vary from a little under a meter to a little bit over a meter. And they say that the big uncertainties are two things. One, obviously, which is the emission reduction path we get on, but the other is, and I think their words are, a deep lack of knowledge of the processes in Antarctica, the ice sheets in Antarctica. And then I saw that a day or two ago, the US NOAA, National Oceanic and Atmospheric Administration, talked about an expectation of a foot of sea level rise by 2050 and at least 2 feet by the end of the century. And so my question to you is, I've been reading about these sea level rise data for a while and various articles that say things are actually going to be much worse than what the IPCC talks about. So my question is about, to what extent is your work and other work in Antarctica already fed into the models that we're seeing, the information that we're seeing from NOAA and from the IPCC, or is it sort of out there? The doomsday part of it is actually something we should see on top of that, something more to be worried about.
So as we all know, thank you. As we all know, surprises happen on this planet. COVID being a recent example. So surprising things happen, and we are so ignorant of what's happening in Antarctica that right now it's a bit of a guessing game, but it's a logical guessing game at this point, in that we know how much ice I'm looking at as I look south here. We know what volume it is, and we know how it could change sea level, but it's putting a number on it by saying how much and when is really what people want to know. And we are just a long ways away from that scientifically. The IPCC, for me, is the gold standard of science, and its comments matter because it's not David Holland's comments, it's me and 3,000 other scientists saying this is our best information that we can provide. And so I like the weight of the IPCC language and its balance. So that's our best information. And we acknowledge in IPCC that the biggest uncertainty in sea level is the object I'm looking at over the bow here, West Antarctica and Thwaites. And we just not there. We just don't understand it. So that information, like the sensors that we put in here to monitor it like a weather station, that information is not yet into IPCC, and it takes a long time to move from observation to theory to understanding to be able to forecast. So we're stuck in a very precarious place for a while to come, where we need to hold on to our seat, because all things seem to be possible, and that's where we stand. We stand in uncertainty, but with plausible concern. Over.
Okay, well, thank you so much for that. I think there are other questions. I'll move to someone else.
Great, thank you. Councillor Youssef, do you have a question?
Thank you very much, Mr. Chair, and thank you, Professor, for taking the opportunity. This is wonderful to be able to communicate with you. I'll be rather brief. A couple of questions. One is, of course, as we see with the melting of the ice on the northern pole, where we're seeing carbon being released into the atmosphere at greater rates as a result of that. Is there a risk that we face as a result from the Antarctic ice being melted, aside from, and not to be little, of course, it is quite a dire risk of the sea level rise and ultimately flooding? So my question is pointing more towards not only carbon, but are we to be concerned about possible bacteria being released into the ecosystem that has previously been encapsulated within the ice? And my second question is on sea level rise, how that will affect not just the coastal and immediately coastal areas, but rather further inland areas where we have, for example, the Fraser River being tidal, as well as the Pitt Lake being also tidal. Over.
Thank you for that. So the first question about the carbon cycle is a fascinating one. As you know, when we look back a few years ago, I was inland near South Pole, and a team was drilling an ice core to the bottom of Antarctica. And you may know from ice cores, we can look back like a million years, and with every slice, we can see the temperature and carbon dioxide on the planet in the past. And what we see in those records is that carbon dioxide and temperature are linked. And what has happened mostly in the past is that the temperature of the planet has changed, and then the carbon cycle has followed by about 500 years later and changed. So our past climate has largely been driven, in many cases, by the sun and the earth becoming closer and further as our orbit changes. But that subtle change kicks off a very large change in our carbon system, CO2, on the planet. And it's written crystal clear in the ice records of Antarctica. What's really surprising about the last 100 or 200 years is, for the first time in a long time, carbon dioxide is now leading temperature. We are pumping carbon dioxide in the atmosphere, and we've kicked it up quite a bit from 280 parts per million to now crossing something like 400. So we've massively increased carbon dioxide, and it looks like the temperature of the planet is responding. So we are in terra incognito of science, of how, like, my part is change air temperature and study physics. How does it change ocean and ice? But it gets really interesting when you get about the feedbacks and you say, well, that's going to affect carbon dioxide, which is going to amplify or de-amplify that effect. And then carbon dioxide and carbon cycle ties in itself to life on the planet, and the blooms that occur in the Southern Ocean and all of that. So a fascinating question. I don't have an adequate, other than everything is linked so tightly. Changing any one causes every other part to change. The second part is about inland rivers. That's also true. As the sea rises and brings salt water inland, certainly along beaches, as it runs over those and you have saltwater intrusion. I suspect there could be some impact on rivers, but I really can't say any more about that. Over.
Thank you very much, Professor. Fair winds and following seas. Over.
Thank you very much.
Repeat, over.
Well, thank you very much. Were there any other questions? I don't see any other hands. Director Hawking. You're muted. You're muted, Director Hawking.
Thank you very much. If I could have one follow-up, and this gets back to the Thwaites Glacier itself and the cork in the bottle. So I appreciate that as you know, it's unfortunate, but as Thwaites is melting, it's not changing sea level rise. It's like an ice cube in a glass because it's already floating. But the cork issue is worrisome, obviously. Can you give us any, like, to understand the speed that this will happen, like how quickly will that inland ice be moving towards the ocean and start raising sea level as it melts? Is this something that we're talking about decades, a century? What, a little bit about that, if you could, please. Over.
Yeah, so it's, thank you for the question. It's not years. I don't see it happening in a decade, but it's when we start talking about multiple decades, then we move into the possibility of extreme change. And certainly when we start talking about a century or more, then it's almost very certain that Thwaites will be ice that's gone and have affected sea level. Recently, in the early 2000s, on the other side of Antarctica, on the Antarctic Peninsula, you may have heard of the Larsen ice shelf. And that ice shelf disintegrated in about a month. It was there for a very long time. And in 1 month, because the Antarctic Peninsula is warming at the same rate as the Canadian Arctic. Where I am, I'm a little bit more south in the peninsula, and here it's still kind of cold. The peninsula warmed up, and that ice shelf went, and then the ice behind it on the land, the grounded ice, sped up by a factor of 10. And that caught the world science community by surprise, because everyone thinks glaciers are these slow-moving things, which they certainly are. But they respond rapidly to changing conditions in the air or ocean, and they're kind of this pent-up energy or pent-up mass that is there and unstable. Another analogy is in Greenland in the late 90s. Some of you may have heard of a glacier in Greenland, the world's fastest glacier, called Jakobshavn. What happened there is that in 4 years, that ice shelf disintegrated in Greenland. It's gone. It was caused by the Gulf Stream waters suddenly took a crack at Greenland. Typically, Gulf Stream waters largely head towards Europe, but the winds, as I said, in the atmosphere changed in the late 90s, and whether natural or human, it's a separate question. Winds changed. The Gulf Stream crashed into Greenland, lit it on fire, and that glacier ice shelf went, and then Jakobshavn inland ice sped up by a factor of 4 or 5 within 2 or 3 years. So the changes are very, very fast in terms of speaking about glaciers. So those are some little things we've seen in the last few decades that has caught my community by complete surprise, because we never thought things could change so fast. But we've seen them with satellites, and we've measured the ocean currents, and it's all very, very real. So the short answer is we should keep our eyes open, wide open, because rapid change can happen. That doesn't mean it will happen. We're doing the research to answer that. Maybe it doesn't, but there's definitely plausible reason to think it could. And if it does, I'm not really sure what we could do about it, because this ice I'm looking around in this continent is absolutely massive piece of ice. And I don't think we could, and I don't think we would necessarily want to think about geoengineering this. I think this might be outside humanity's scope for dealing with and responding to. Over.
Thank you very much. Thank you very much. Much appreciated.
Great. Well, thank you very much. I think those are the questions. And maybe Chair Dhaliwal, do you want to offer, or Chair Carr, sorry. Thank you. And then we have a surprise at the end on the video.
Great. Thank you so much, Professor Holland, for your time, for the work that you're doing. This has been fascinating. Wish we could have even longer, but we're very, very grateful for this time. I'm just wondering if you have any final comments that you wish to add before we sign off.
Yes, I do. I lived in British Columbia, beautiful British Columbia, as a student back in the days, and I love the province of British Columbia, and particularly admire the sensibility of the population towards the environment, and it comes through when you're talking to me. And so I have great respect for what you do and the way you're concerned and your approach to the way you do things. So I would like to salute you all for your interest and your love of our planet. Over.
Thank you very much, Professor Holland, on behalf of... Thank you very much, Professor Holland. And on behalf of Metro Vancouver Board of Directors, I want to thank you, and also Denise Holland for joining us and also helping us with setting up this call. We certainly appreciate that. And before we all go, I just want to turn it back to our Commissioner, Jerry Dobrowolny, to just introduce the next part of the program.
Great. Well, thank you very much. We've got a little bit of a surprise. It's nothing on the scale of what Professor Holland has been speaking to, but for all of our elected officials, we do have our very own glacier here in Metro Vancouver. So we have a short video on the Coquitlam Glacier in the Coquitlam watershed, and unfortunately, that glacier has been receding and shrinking as well. So maybe I'll ask the staff now if they can just play. It's just about a 2-minute video, and then we'll wrap up.
A Metro Vancouver team is headed into the Coquitlam water supply area to assess the last glacier in the region, the Coquitlam Glacier. The team is led by Dave Dunkley, a geoscientist with Metro Vancouver who has been studying the Coquitlam Glacier for over 15 years.
The first time I saw the glacier was in 2005 from a helicopter, and I went, whoa, we got to have a look at that. And then I came here first in 2006 for just about an hour. The ice was up halfway up this slope on the left here and on the right here, and it's probably over my head where I'm standing.
A glacier's changes in length, height, and width over time are one of the clearest indicators of environmental shifts due to climate change.
As it warms up, our snowpacks are getting less deep and they're melting, and the snow line is going to move up in elevation.
Metro Vancouver placed a time-lapse camera to monitor the glacier between July and October of 2021. These images show the seasonal snow on top of the glacier melting. The glacier's actual melt is much slower and happens over decades. Dave Dunkley has noticed significant changes in recent years.
When we were here 2 years ago, I had noticed a crevice on the glacier that seemed to be breaking off or calving off from the main glacier up here. It's official now. It's pretty clear that this is getting wider, this crevice, this crack, and it's about 1/2 meter across. And it looks to be 20 meters down, and you can see water flowing, and it's just under a glacier, a little creek that's flowing out of here. So it's quite stunning, quite spectacular.
While the glacier does not play a significant role in providing water for the region, the pace at which it is melting illustrates the changes occurring in our water supply area due to climate change. Understanding these changes is essential to ensure continued, reliable, and sustainable delivery of high-quality drinking water to the region.
It's an iconic symbol, and it's important to study this, and that's what we're doing at Metro Vancouver.
Thank you very much, staff, for this very short video. Thank you. I did not realize we do have our glacier right here in Metro. Thank you for that. And thank you to everyone who attended today's discussion with Professor David Holland. We look forward to our continued work together to address sea level rise and take action on climate change. With that, I want to say thank you to Professor Holland. I know you're still on the line there, and we wish you the best and safe journey, and take care. Enjoy the rest of the weekend. Over.
You too. Thank you so much. Over.